the interference of light and how Thomas Young developed the double slit experiment. In the picture, we see a blue morpho butterfly. Okay. Now, on this surface of the butterfly, we see a blue color, but on the other side, we see brown and tints of yellow. Now, what causes these colors? In the video shown, we can see that on this side, we see the spots or the eyes of the butterflies. On the wings, we see the spots, and they have a brownish tint. But on the other side, we see a blue tint, right? The bluish color on one side and the brown and yellow tints on the other side, right? Now the brown and the yellow tints are due to the pigments, color pigments on the wings, but this blue color is due to the interference of light on the nanoscale structures of the wings. It is a beautiful example of interference of light in nature. Now, the superposition of two coherent waves gives us the intensity of light to be I equals I0 cos square delta by 2. So this was the mathematical expression that we have derived. Here, we can get the maximum intensity of 4 I0, that can be written as 2 square I0, and the minimum intensity as 0. Now, if we have n coherent waves, our I max will be n square times I0 and I minimum will be 0. In these two cases, we can observe the interference of light where there will be alternate maximas and minimas, or alternate bright and dark regions. Now, what happens if incoherent waves superimpose? So for the superposition of incoherent waves, we get the average intensity of light, I average, and it is calculated by taking the bracket of I. Now here, the equation that we take into consideration is I equals I1 plus I2 plus 2 root of I1 I2 cos delta. This is because we had simplified it into I0 cos square delta by taking into consideration that I1 and I2 having the same amplitude I0. Okay. So for incoherent waves, they need not have the same amplitudes. So I1 will not be equal to I2. Thus, we take this equation into consideration, and taking the average of this equation, the bracket of this equation, I will take the bracket for each term. Okay. So the bracket of the first term I1. I1 means the instantaneous intensity of the first wave. So it is not an averaged value, it is an instantaneous value. You cannot take the average. It is like a constant. Okay, so it is I1 itself. Similar is the case for I2. So the second term is again I2 plus twice of root I1 I2. That is remaining as a constant. And the next term, cos delta. Cos delta is a variable. Okay, so bring into mind the nature of the cos delta curve, and the average of cos delta will be 0, right? Okay, since that term averages to 0, the third term will vanish. Hence, I average is equal to I1 plus I2. And this will just produce uniform illumination. So the superposition of incoherent waves just produces uniform illumination. Now let us see how the Young's double slit experiment was developed. In 1665, it was Grimaldi who first attempted to produce an interference pattern. What he did was, he allowed sunlight to pass through two slits. Okay, so he produced two beams from sunlight and allowed those beams to interfere. But he did not view any interference pattern. Okay. Now, Thomas Young was the person who first successfully demonstrated interference of light. What he did was, he made sunlight to pass through a narrow slit first. Okay. So initially, he made light to pass through this slit, and when light passes through a narrow slit, this sunlight has a broad range of wavelengths, okay. It is not monochromatic, it is not coherent. That was where Grimaldi went wrong. We need coherent lights to superimpose to produce interference. So here Thomas Young first passed sunlight through a narrow slit and made it almost monochromatic. When sunlight passes through a narrow slit, only a short range of wavelengths will be allowed to pass through. So he made sunlight to become monochromatic by passing through a single slit. Now this becomes your source of light, and this light is again passed through two slits, producing two different beams of light, and when they were made to interfere, you can observe a pattern on the screen. And the few colored fringes were observed in this experiment. It was as seen in this picture. The central bright white region surrounded by colored rings on both sides. Now, how do we set up Thomas Young's double slit experiment in the lab? Okay, for that, we allow monochromatic planar wave, that is light from a laser source or a monochromatic source like sodium vapor lamp. It is allowed to pass through two slits. So when a planar wave passes through two slits, we get cylindrical wavefronts emerging from the slits. And these wavefronts, when they are allowed to superimpose, the crests meet the crests, or the crest may meet the troughs of both the waves and produce alternate bright and dark regions on the screen. So the primary light sources that we can use is a sodium vapor lamp or any laser. We should use a monochromatic source. Now the secondary light sources are the slits. We use two narrow, closely spaced slits. We should have a detector or a screen to view the pattern, and the pattern is obtained as such. The interference pattern will be alternate dark and bright fringes that are equidistant from each other. This is the nature of the interference pattern. Now let us do the mathematical way or the mathematical derivation of how to interpret the interference pattern obtained from this experiment. For that, let us assume we have a light source, a monochromatic light source. It is kept in front of a double slit, okay? And we have a screen placed farther away from the double slit. Let the double slits be named S1 and S2, and they are small d apart from each other. The double slit and the screen is kept at a capital D distance, which is very much larger than small d. Now let us draw a perpendicular from the double slits to the screen. So the perpendicular from S1 will meet the screen at E, and let M be the midpoint of S1, S2. Then let us draw a perpendicular from M to the screen, it will fall at O. Usually this is assigned as the optic axis. And let us draw a perpendicular from S2 to the screen. It will meet the screen at F. Now the distance OE is half D2 and OF is half D2. Now let us assume a point anywhere on the screen as P, and the distance of that point from the optic axis is X. Now let us draw a light ray from S1 to P, and it forms the line S1P. Another light ray is drawn from S2 to P, and it forms the line S2P. Now a reference line can be drawn from M to P, and it is MP. Now let us draw a normal from S2P to S1. Okay. The angle made by the optic axis with MP is defined as theta. If this angle is theta, then the angle S2 S1N will also be theta. Now, we are going to define the path difference between these two light rays from the double slits. So we have a light ray from S1 and another light ray from S2. And the path difference between these two rays will be the longer ray minus shorter ray, that is S2P minus S1P. Now to calculate that, first let us calculate S2P square minus S1P square. Okay, so what is S2P square? Now consider the triangle S2PF. In that, S2P is the hypotenuse and PF is the altitude, S2F is the base. Hence I can write S2P as base square plus altitude square, right? So that is written here. We have altitude as x plus d by 2 the whole square plus base square d square. So this term is the S2P square. Now what is S1P? Consider the triangle S1PE. In that, S1P is the hypotenuse and PE is the altitude and S1E is the base. So hypotenuse square can be written as altitude square plus base square. Altitude is x minus d by 2 whole square plus base square d square. Okay. Now substituting these values in this equation, I can write S2P square minus S1P square as x plus d by 2 whole square plus d square minus S1P square. So x minus d by 2 square. Here it was plus, so dividing the minus term we get minus d square. So d square cancels out. The next line, we can expand the x plus d by 2 square and x minus d by 2 square. So we get x square plus xd plus d square by 4 minus of x square minus xd plus d square by 4. You can write along with me. And this is equal to 2xd. All the other terms can be cancelled out. Okay. So, here on the left hand side of the equation, it is of the form a square minus b square, right? So, I can rewrite it as a minus b into a plus b. Okay, so that's what I've done in the next step. Here I have rewritten it as S2P minus S1P into S2P plus S1P. And this is equal to 2xd. So in the next step, I write S2P minus S1P is equal to 2XD divided by the sum S2P plus S1P. Now what is S2P plus S1P? S2P, well, usually the distance capital D is very large, and it implies that S2P and S1P are almost parallel to the optic axis. So in that case, S2P can be approximated to capital D and S1P can be approximated to capital D. Okay, so here the sum will give you 2D. Even though they can be approximately equal to capital D, there will have very small differences. So that is why here we don't take this difference value S2P minus S1P to be 0. We don't take that because even that small difference creates the interference pattern. Okay, so we need to find that small difference, and in the summation term we take it to be approximately equal to capital D. Okay, so here the difference, the path difference is obtained as XD divided by capital D. Hence path difference is directly proportional to the distance between the slits and inversely proportional to the distance of the screen from the slits. Now, in the Young's double slit experiment, what we view is an alternate bright and dark regions on the screen. If we are to draw the intensity distribution curve here, we will get the curve in this form, right? I hope you can draw along with me. So this is the pattern of the intensity distribution curve that we obtain on the screen. Now, let us assume that at P we have a bright spot or a bright fringe. So in order to form a bright fringe at P, it should satisfy the condition for constructive interference there. Okay, so the condition was path difference should be an integral multiple of lambda. You should always remember this. We will be using this time to time. So the path difference should be an integral multiple of lambda, where n can have values 0, 1, 2, 3, etc. So equating the value for path difference that we just derived, we get xd by d is equal to n lambda, that is x of the bright fringe xb is equal to n lambda into capital D divided by small d. Okay, now when n is 0, x will be 0, and this corresponds to the central fringe. It is called the zero order fringe. Now when n is equal to 1, x is equal to lambda capital D divided by small d, and this is the first order bright fringe. You get the first order bright fringe. This one. Okay. These two are the first order bright fringes. Now when n is equal to 2, we get x is equal to 2 lambda capital D divided by small d. This is the second order fringe, and the second order fringe is obtained as these two fringes. Okay. Now the fringe width beta can be calculated as the distance between two consecutive bright fringes. Okay, so that will be calculated as xn plus 1 minus xn. So here the difference in the integers is just 1. So it represents two nearby fringes, and the difference between two nearby fringes will give the fringe width. That gives beta to be equal to lambda capital D divided by small d. Now, let us assume a dark fringe to be at the point P. The condition to be satisfied for destructive interference at P is that path difference should be an odd integral multiple of half wavelength. That is, xd by d should be equal to odd integral multiple 2n plus 1 of half wavelength lambda by 2, and this gives the x at a dark fringe to be xd is equal to 2n plus 1 by 2 into lambda capital D divided by small d. Now to find the positions of the dark fringes, we give the values of n as 0, 1, 2, 3, etc. So when n is 0, we get x is equal to lambda capital D divided by 2d. This is the first order dark fringe. Now when n is equal to 1, we get x is equal to 3 lambda d by 2d. This is the second order dark fringe. When n is equal to 2, we get x is equal to 5 lambda d divided by 2d. This is the third order dark fringe. Now fringe width beta is given as xn plus 1 minus xn, and this gives beta is equal to lambda capital D divided by small d. This picture shows the interference pattern produced by using different monochromatic sources. So if we use a red light source, we get the interference pattern shown in the top. If we use a green light source, monochromatic means if we use the light source of wavelength around the region 550 nanometer, that is the wavelength of green light, we get the pattern shown in the middle. And if we use a light source, monochromatic light source of wavelength in the blue region, we get the interference pattern shown at the bottom. Now, fringe width is the distance between any two consecutive bright or dark regions. The width of a bright fringe will be equal to the width of a dark fringe. Now the fringe width is independent of the order of fringe n. Beta, fringe width is dependent of different values. First, it is dependent of wavelength of source light, lambda. That is, beta is directly proportional to lambda. It is evident in these pictures. Now for red light, we can see that the fringes are spaced farther away from each other. That is, fringe width is larger. Now for lower wavelength in the green region, we can see that the fringe width reduces. Now again for lower wavelengths in the blue region, the fringe width decreases. The fringes come closer. So from these images, it is clear that beta is dependent on lambda. Again, fringe width is dependent of the distance of the screen from the slits. That is, beta is proportional to capital D. As capital D increases, the fringe width will increase. Beta is inversely proportional to small d. Okay. So if the distance between the slits increases, the fringe width decreases. Okay. So these are the comparisons of the variables upon which fringe width depends. Kindly refer your study materials to understand more. That's all for today. Thank you.